That's fine. It's not next Thursday. Hydraulic jump day is the following Tuesday. Would you? And you wouldn't be disappointed if you did. You got your wig? Somebody at eBay wondered, why all the blue wigs to West Virginia? You know, it's like the blue crystal meth from Breaking Bad or something. Blue wigs. I don't know. Yeah. They're going to raise their price on blue wigs. Probably is what's going to happen. So I looked, and it seemed like there were a lot of submissions for the pipe network sizing as of yesterday when I looked most recently, and I'd imagine the rest of you uploaded it to MU Online by now, I hope. And we're going to talk about reservoir sizing briefly today, and the draft submission for that will be Tuesday, April 8th. Also Tuesday, April 8th is hydraulic jump day, and I had originally anticipated us doing that on Thursday, April 10th. That's what I announced previously, but I'm going to be down in Clemson working on the FE exam that day, so we need to move it forward to Tuesday. Boy, now that exam 2 date, that doesn't make any sense, does it? Tuesday, oh, what is this? Tuesday, April 7th? No, that's not right. Anybody have a copy of the schedule with them? Tuesday, okay, yeah, that's right. Yeah, okay, so the exam is a week from, yeah, it's on Tuesday the 1st, and that's when homework 10 is due as well. All right, yeah, it threw me off for a second because I was talking about a different Tuesday, the 8th, but 7 plus 1 is 8, so all's right in the world. Okay, those are the announcements. We've got a lot going on in the coming couple of weeks. But then class on Thursday the 10th will be online, so that's always a little bit of day off for you, I guess. Some of you are going to be gone to the Virginia's conference next Thursday, is it? A week from today? And as always, I'll post the recording online. I hope you got my email that those missing recordings are online, so there won't be any gap in the coverage on what's on the YouTube stuff. So today we're going to talk about reservoir sizing, channel expansions, weirs and spillways, and go into the lab and do a brief hands-on demo. So we've got a lot to cover. Any questions on the scheduling stuff before we get into reservoir sizing?
What was the last? What does this test start?
Chapter 10.
Is it our
Chapters 10 through 12. Yep. And so it's just the open channel stuff. You know, it starts with the channel geometry in Chapter 10, the Manning's equation in Chapter 11, and now here the stuff we're doing about specific energy in Chapter 12. Those are the three big ideas that'll be on the first midterm. All right. One other announcement is that assessment day is March, when are they doing the hot dogs and all that? April 8th. So after, I guess before coming to this class, you could stop by and get hot dogs and Pepsi on the plaza. They've got online surveys for people to take, so I'm sure that you've seen posters about this up, and they wanted us to announce in class that they love to have you participate in assessment day. So there you are.
What happened to your mid-semester?
Yeah. Well, I implemented a lot of the things that were mentioned there. For example, the notes, you know, they don't have the lines on them anymore, so I tried to apply some of the suggestions that I got. Let's talk about water storage volumes. You already have hopefully designed your system so that at maximum flow you don't see anywhere in the network with more than 850 kilopascals, and at the actually, you'd see that at no flow is when you see the max pressure, and you see the minimum pressure at the peak flow. That's the range that you're supposed to be within. The water storage tank partly exists to provide pressure for your network, but it's also used to provide water when the city is consuming more than can be produced by the artesian well that exists up on the hillside. And here's what we know about the water demand in the city. Here's my digitization of that top curve, and you submitted a similar thing for one of your homework assignments where on an hour-by-hour basis. You said what percent of the peak that was. You can see that here at 7 o'clock, 8 o'clock, I'm saying that's the peak, so it's 100% of the peak at 7 o'clock. And then at midnight, since it's 100 divided by about 270 at midnight, that is 36% of the peak. So this is a ratio of, at any hour of the day, the flow rate demand versus the peak demand. And the highest point of that curve is it's the design flow that you identified in your demand estimation. So the blue line that's pictured there illustrates the average flow rate that's coming into the tank. We're going to have a water storage reservoir where the inflow to the reservoir is constant and the outflow varies. And so what happens to a tank when the inflow is constant and the outflow varies? Well, there's going to be a point where after a long day, that tank is almost completely empty. You know, after the demands have been really high through the day. But then as people start going to bed at night, then the tank is going to start filling. And this is the in line, and here is the out. And so it looks like about 11 o'clock maybe is when it starts to fill. Now I just eyeballed that blue line. The location of that blue line is meant to be so that the area above the curve, you know, the area under here and here is equal to this area between the blue line and the curve and that area. And so the time at which the tank begins to fill is just before midnight. And so the out is smaller than in, and so the water level starts to rise. And the tank is pretty nearly full, and then all of a sudden the demand starts increasing after the middle of the night. Then the outflow is greater than the in, and then through the day the tank begins to drain. And there's a short period of the day after people get to work and aren't at home any longer. There's a short period of the day where maybe the tank is filling again, but then it starts to drain. I'm sorry, I guess this is where the tank is filling, right here. But then when people get home and start consuming more water, it starts to drain again. So we're going to go through the process of saying how big should the tank be if we know that there's a constant inflow, but the outflow varies. In the assignment description I gave you for the project, what I said is that the flow rate from the spring towards the tank is equal to the average daily flow on your design day. And so let's just say, for example, that you've got an inflow of 254 liters per second. Then how should the tank be if your peak demand is 400 liters per second? So in other words, in this illustration, what I'm going to show you is how big the tank would need to be if the flow coming in was 274 liters per second. That's the blue line there. And then the peak flow rate, when the greatest demand is actually happening, is 400 liters per second. The procedure I'm going to follow, and remember that this is recorded, and so you can come back to the Excel manipulations I'm about to do and do it yourself for your own flow rates. But we're going to look at this digitization that's available and try and find out when the Q in is greater than the Q out. And we're going to have to reorganize that list to make it so that the Q in is greater than the Q out is at the top of the list. And then for each hour, we're going to find out how much water came in, how much water came out, and then the difference between the two is either how much water accumulated in the hour versus how much water left the reservoir in the hour. And then the point where there was the biggest cumulative difference between the two tells us the amount of water that needs to be stored by the reservoir. So I'm going to start up Excel, and hopefully you've saved your spreadsheet where you put together the curve. You know, hopefully you've still got your assignment where you did this one. So I'm just going to copy and paste that and put it into Excel. And you've got the same thing. Looks like it pasted a little bit weird. Let me paste it and then choose the text. There we go. All right, so in this case, I'm going to find the flow in. The flow in from the spring is 270, what did I say in this illustration here? 253.7. 253.7. And then the flow out, the peak flow out is 400 liters per second. And so I can say for each hour what is the flow in, the flow out, and they're just based on the flow in, of course, is constant, so it will just be anchored up to that location. And then the flow out is going to be this anchored, nope, wrong one. It is the 400 liters per second anchored multiplied by the percent of peak. And so at 12 o'clock, I've got 144 liters per second because it's only 36% of the peak flow rate. Double click to bring that down. So in the evening, you go to the evening hours and you find out when, for the first time, is the flow out less than the flow in. In other words, when is the reservoir going to start filling up after having been draining all day? And so here you can see at 11 o'clock is the first hour where the flow out is less than the flow in. And so what I need to do is I need to add a line, and I need to move from the 11 o'clock row up to the top, so that I'm starting with an empty reservoir, and then I assume that at 10 o'clock and 59 minutes the reservoir is virtually empty, but then at 11 o'clock all of a sudden the flow in is greater than the flow out. So now I want to have the volume in terms of liters and the volume out. And actually, it may be more convenient if I find it in terms of cubic meters. And so I'm going to say cubic meters. Okay, so the volume in is going to be the flow rate in divided by 1,000 to convert between liters and cubic meters. And then I have to multiply by how many seconds there are in an hour. Because we're saying for the entire hour, the entire 11 o'clock hour, there's 3,600 seconds. And so assume that you've got that flow rate coming in over that entire 3,600 seconds. So I've got 913 cubic meters of water that came in. And I can do the same thing to find out how much water came out. I'm just going to have the flow rate out divided by 1,000 and then times 3,600 seconds. And that tells me how many cubic meters went out of the system during the time increment in question. I can just double click and it'll apply those calculations all the way through. And then I need to look at the difference between the two. This is so far, not the cumulative, but just the difference between the in minus the out. So in minus out tells me that this is how much accumulated in the tank during that 1 hour period. So the tank has to be at least 179 cubic meters to hold how much water was net accumulated during the 11 o'clock hour. And so I can drag that through and find the difference just on an hourly basis. You'll notice that some of them are negative, which means that the water was going down. Some of them are positive, which means the water level was going up. And so then there's another column that's cumulative difference. And cumulative difference, what that is we're trying to keep track of, in the first hour it's just how much was there, but then in the next hour it is how much was in the previous hour plus the difference from the hour that we're in. And so, for example, at the end of 11 o'clock, I had the 179 cubic meters. And then I had another 395 cubic meters, and so I add those two together, and at the end of 12 o'clock hour, I've got 574. And so that process continues, and you can see that it sometimes goes up, sometimes it goes down. There appears to be an error here. What's the average of the flow out? 256.3. It must just be the round off that I'm doing here. Yeah, that's exactly what it is. When I copied this table from, when I copied the table from here to Excel, I lost my third digit of precision for the percent of peak. You won't have this problem when you're working on yours, but the way that you know that it has converged to be the correct, that the answer is right, is when it goes to 0 at the end. Let me just make sure what's going on here. Yeah, so you'll notice that the volume is going down, and then it increases again. And so the size of the tank that's required is the largest of the cumulative differences throughout the day. And so if we find what is the max of that, then you'll know how big the tank needs to be. So there's a formula equals max, and you can put it in here, and it sees 2304 is the largest of these differences through the day. I did Shift, Control, and the down arrow, and it goes to the bottom of the list. Yeah. So that's the process of finding the reservoir volume that's required. Is you go through and you find the volume that came in and the volume that went out, the difference between the two, so you know how much net during the 1 hour period came in versus went out, and then you find the cumulative difference over the entire course of the day. Any other questions about that?
Do you have any kind of factor?
Yeah, sometimes it's common to add, in this case, a 25% safety factor, and so the size that you design for would maybe be 1.25 times what you found, 2880. And so then what you'd look at maybe is the diameter of the tank that you're going to use and how tall the tank would have to be in order to give you the design volume that you come up with. Any other questions on sizing the reservoir? All right. Well, where we left off was talking about channel expansions, and we're going to take a look at an example where we want to find the new flow depth downstream, where we are going to factor in a C value that accounts for the energy loss due to the expansion. And this is somewhat akin to accounting for local losses, you could say, because there's turbulence induced by the channel transition. And so we're going to find out what would be the new flow depth downstream when the channel goes from being 3 meters wide originally to 5.7 meters wide after the transition. We're given in this problem that the flow rate was 9.9 cubic meters per second. We can find the flow per unit width at 1 by using the 9.9 cubic meters per second and the channel width of 3 meters. And that gives us 3.3 meters squared per second. And from that, calculate the critical depth, because this is a rectangular channel. It's the flow per unit width squared divided by G, and that to the 1/3 power. So we've got 3.3 meters squared per second. Square that, divided by 9.81 meters per second squared. That's 1.035 meters. The depth at 1 is already known to be 2.75 meters. And so y1 is greater than yc. And what does that tell us about the flow regime? Subcritical, right. Subcritical. And why does it matter that the flow is subcritical? That's right, yeah. The flow regime upstream governs what the flow regime will be downstream. And so in other words, you know if the water is going to get deeper or shallower. Because remember, the specific energy diagram shows us that when there's a step or a transition like this, it could go either way. It could get deeper or it could be shallower. But it depends on the flow regime upstream. The flow per unit width at 2, Q divided by B2, we'll do that and get 1.737 meters squared per second. Now, we're going to apply the energy equation where we've got y1 plus the flow per unit width at 1 squared divided by 2g y1 squared is equal to y2 plus q2 squared 2g y2 squared plus c, which is the energy loss factor times the velocity head at 2. And we're writing the velocity head in terms of the flow per unit width because we don't yet know what the velocity will be at 2, and we don't know what the depth will be. And so we're writing the velocity head in terms of the unknown depth at 2. So we can substitute in the values that are known. For example, the depth at y1 is 2.75 meters. We put in the flow per unit width of 3.3 meters squared per second. Square that. 2g is 2 times 9.81 meters per second squared. And the depth at 1 is 2.75 meters, which is squared, will be equal to the unknown depth y2 plus 1.737 squared divided by 2 times 9.81 times y2 squared plus the C factor that we're given here. The transition is causing energy loss, and the C factor that we're given is 0.45 times this same velocity head. 1.737 squared divided by 2 times 9.81 y2 squared. So the left-hand side of the equation, if we add all of those constants together, it is 2.823 is equal to y2 plus 0.223 divided by y2 squared. And then we can rearrange that by multiplying each term by y2 squared. We get y2 cubed minus 2.823 y2 squared plus 0.223 is equal to 0. And solve for the roots. Select the deeper of the two non-negative roots because the deeper represents the subcritical root. And so when this channel expands, the depth was 2.75, and it's going to go to 2.79. It's going to actually get deeper because it expanded. We might have reasonably thought that since it's expanding, maybe it'll get shallower because, you know, conceptually, you might think of it has more room. You know, it's going to get shallower because you're not forcing it into such a narrow passageway, but actually it got deeper when we look at solve for the energy.
Why do you say that?
Well, for one thing, the velocity slowed down. When we made it wider, the velocity slowed down, and so to maintain continuity, you know, if the velocity decreases, the cross-sectional area has to go up. And so the depth increased and the channel gets wider. All right, we're going to talk about spillways now, and here's a picture of the Grand Coulee Dam, which is along the Columbia River in Washington State. It's an enormous structure that generates really a lot of hydroelectric power for the entire Pacific Northwest. The Pacific Northwest has some of the most inexpensive electricity in the entire United States, whereas we pay about 11 cents per kilowatt hour for coal-based electric power in West Virginia and most of this region. They're usually paying around 5 or 6 cents per kilowatt hour for hydropower. They're fortunate to have a big river with a nice tall head drop so that they could generate a lot of electricity. You can see that when the water goes over the spillway, there's a really steep drop along the spillway face, and we've talked about this as being a location that induces a hydraulic jump. You know, out in nature, water coming off the top of a spillway accumulates so much velocity that then it has to dissipate all of that energy when it gets to the bottom. What we're going to be looking at today is trying to figure out the height of the spillway required and the relationship between the water level above the spillway and the flow rate. As you can see from this diagram, the water actually sort of pools over a spillway crest. And because of the curvature of the spillway crest, you can express a curved spillway as though it was a sharp-crested spillway, a sharp-crested weir. You know, the dark shaded lines here represent hypothetically the performance of the flow over a sharp-crested weir that's equivalent to the actual spillway that's there. And just as a general rule of thumb, they say that there's a relationship between the H, which would be the water height above this theoretical sharp crest, and H sub D, which is the actual physical elevation of the water above the spillway crest. And there are equations that relate, in general, the flow rate of the water over the spillway, both in terms of it being an actual curved spillway shape, which is this based on the H sub D, or the hypothetical idea of it being a sharp-crested spillway. And so just to introduce the idea of spillways to you, I thought we'd take a look at this example and calculate how high the water levels would be if we were going to try to be passing a 100-year storm over a 300-foot-long spillway. You know, these are typical flow rates for large reservoirs. Maybe the Columbia River would even be larger than this potentially as far as a 100-year storm. But let's say that we had a water level that's allowable as 4350, and you wouldn't want the water level to get any higher than that, maybe because there's property that would be threatened if the water level got higher, homes that are along the river or farmland that'll be flooded. And so we don't want the water level that's indicated here with the triangle and the little hash lines to get any higher than 4350. We've got a flow rate Q of 38,000 cubic feet per second, a spillway length of 300 feet, and that parameter is into the page. It's, if you're looking at the spillway, the L is this length. It's the dimension that is into the drawing as we look at it here. And we want to know what elevation should the spillway crest be built. And so the equation that we'd use for that is Q is 3.97 L times h sub d to the 3/2 power. And that's easy to rearrange to solve in terms of h sub d. We're going to be finding the height of the water above the spillway crest with this. And so h sub d is simply going to be q divided by 3.97 times L, and that to the 2/3 power. And we can substitute in the information that we've been given of 38,000 cubic feet per second, 3.97 times the 300-foot spillway crest length, and to the 2/3 power. So that works out to 10.06 feet, and then the spillway crest should be 10.06 feet below 4350, because the water level can't be any higher than 4350. That's sort of our upper elevation datum, and the spillway crest elevation needs to be, if this h sub d is 10.06, then the elevation of the spillway crest will be lower than that. And so the spillway crest will be built at 4350 minus 10.06, and so it will be built at 4339.94 feet spillway crest elevation. In the lab today, we're actually going to look at a sharp-crested weir. Unfortunately, we don't have a spillway to look at, but
How far back will that fluid occur to be more fluid? I guess
all the way.
that 10 foot?
Yeah, because here, this isn't on a river, this is on a reservoir.
Yeah.
Yeah. Yeah. So it's not like an obstruction that might be in a channel that's on a slope and it'll only disturb the water part of the way. That would go all the way back. A broad-crested weir is something that we're going to look at in the lab today. And a broad-crested weir works by inducing critical flow over the weir. Remember, we talked about how there's some step up, a delta Z, that is the critical delta Z. And the critical delta Z is that step up that there is no longer enough specific energy to get over that obstacle. And so the way a broad-crested weir works is by being a step larger than the delta Z, which forces the delta Z max, which forces the water upstream to pool, and then it only pools as much as is required to force critical flow over the obstruction. And so its functionality, they're used to quantify flow rate. You know, the whole point of a broad-crested weir is that if you measure the critical depth over the weir, then you can use this equation and find out what the flow rate is. It's a flow measurement technique. It's kind of easy to measure flow rate with a pipe, for example. They have these magnetic flow meters where it's like a collar that would go around a pipe, and it measures the magnetic signature of the mass that's going by, and you can quantify the flow rate with a magnetic device for an enclosed pipe. But you can't use that same approach for a channel. It doesn't work because it's open to the air and the channel width changes and so on. But if you force the flow through a section where there's a broad-crested weir and you measure the critical depth here, you'll notice from the formula that the flow rate will be some coefficient of discharge, which relates to the amount of energy that's lost as water flows over this obstruction. You know, the C sub D just accounts for the turbulence as water, which was maybe not necessarily laminar, but the flow depth was set up and the channel bottom caused pretty regular flow pattern. Then you have this sudden step up, and that causes a lot of eddies and probably energy loss that's accounted for the C sub D. B here is the width of the channel. Square root of G obviously is the square root of the gravitational constant. And then 2/3 of H, where H is the amount of specific energy above the Broad-Crested Weir. And so it accounts for both the flow depth and also the velocity head. And what we know is that the critical depth accounts for 2/3 of the entire specific energy. When the conditions are critical, you can measure the flow depth, and that's 2/3, or the velocity head is 1/3 of the specific energy. And so this substitution here of y sub c is 2/3 h. If we just put y sub c in this formula, that's actually the formula that you're going to use in the lab today to try and quantify what's the flow rate going through the flume. And so we're going to use the Broad-Crested Weir as another way of quantifying the flow rate through the flume. You're going to take the measurement of the critical depth and compare the flow rate that you get with the Broad-Crested Weir equation to the flow rate that you can measure using the stopwatch and the volume measurement on the hydraulic bench. The C sub D can be estimated as shown here. There's a formula. This is really dependent on the width of the channel, the height of the Broad-Crested Weir relative to the water height. And so this formula is by no means bulletproof. In almost every case, a Broad-Crested Weir would come with a manufacturer-provided discharge coefficient, or you do experiments in the field to find out, calibrate what the discharge coefficient is. And actually, that's a part of what you'll be doing today, is estimating what's the discharge coefficient, not from this formula, but from the measurements that you take of the flow rate and the critical depth. By contrast, a sharp-crested weir, the difference is the broad crest is a really long section that you can measure critical flow over. The sharp-crested weir comes to a point, and it causes water to flow over the sharp-crested weir. And so if we apply the energy equation at location 1 and location 2, here you can see we're setting the energy equal to each other for now, neglecting the energy losses between the two. And we say that at location 2, that's our elevation datum. So allow the elevation at 2 to be equal to 0 in that energy expression. Then you can rearrange the energy equation to solve for the velocity at 2. And this is somewhat similar to the orifice equation when we said that there was water coming out of a small hole on the side of a tank, in the way that we're using the elevation difference and the velocity at 1 to tell us what the velocity at 2 should be. We define the total head, the elevation of the water above the sharp-crested weir, that's h. And so we can also find the velocity at 2 as the square root of 2gh. And oftentimes the velocity head is so small relative to the total energy at 1 that we just actually put the water depth. And so here you can see that h is measuring all the way from this datum to the total energy line. You know, it looks like there's a pretty good gap here between the water surface and the energy line. But if the water's moving pretty slow and the velocity head is negligible, then you can sometimes get away with just measuring the physical elevation of the water rather than also finding what is the velocity head component of that elevation difference. And so that's what we'll do in the lab today, is we'll actually just measure the physical water depth above the weir. And this shows the development of the sharp-crested weir equation. If you integrate the incremental elements of increasing water height of the water that's flowing over the edge, if you slice it up into very small vertical elements and you integrate over the entire water depth from the edge up to the surface, then you ultimately get that the flow rate is a discharge coefficient. The C sub D again counts for energy losses, and 2/3 times the square root of 2g, both 2 and g are in the square root, L is not, and then h to the 3/2 power, where h is the water elevation plus the velocity head. Likewise, just as it was with the broad-crested weir, this estimate for the discharge coefficient is just kind of an empirical observation that isn't always true, and it won't really even be close for the measurements that we do today. I'm going to ask you to find the discharge coefficient for the Broad-Crested Weir that we have in the lab, and this equation won't be a good predictor because primarily our Broad-Crested Weir is very narrow. You know, we're working with pretty small quantities of water, and this is maybe an equation that would be more effective for full-scale sharp-crested weirs that would maybe be used in irrigation and farming out in the real world. A typical C sub D would be 0.62, and so if you combine the typical C sub D of 0.62 along with the constant of square root of 2g, so C sub D, the 2/3, and the square root of 2g, that's sometimes just combined all together as a single C value, and you can see that for both SI and BG units, all three of those terms are combined, and there's a typical C value that you'd maybe be given the back of the envelope type calculations where you're just trying to find broadly what the flow rate might be if you're measuring the height of the water surface. This would be a good place to start for that. The weir that we've got, the sharp-crested weir that we've got, is a contracted rectangular weir. Sometimes these are called unsuppressed if it's contracted. And what it means is that the water is actually only flowing over the edge part of the channel width. It's not the entire channel width that the water is flowing over the edge. You can see that there's like some edge panels here that make it so that the weir length L is different from the channel length B. And that's what we've got in the lab. We've got that the water that's flowing along the bench has, the bench has a certain little trough in it that's fairly wide, has a big B, but then the weir that we're going to be using is only maybe 2 inches in length. L is going to be very small. And so what you have to do when you're using the Weir equation, if this is the Weir equation where we previously had L, you have to substitute in L prime if it's a contracted Weir. And that is the equation that's explained in the handout I'm going to give you now. This demo that we're going to do today requires calculations that'll probably take you between 5 and 7 minutes to complete, and you'll submit it with your next homework assignment. This is not intended to be like a big report or a lot of heavy calculations. This is just something that really wouldn't have made much sense to you if it had been introduced during fluid mechanics. And of course, we don't have a lab in this class, and so I can't give you a lab assignment, not in good conscience anyway. What I can do is just ask you to do a very simple homework problem based on a demo that we're going to see in the lab today. So we're going to look at both a broad-crested weir and a sharp-crested weir. We'll do the broad-crested weir. We'll talk about it first. I'll have both set up simultaneously and maybe have half the class go take measurements on the broad-crested weir while the other half is taking the measurements on the sharp-crested weir. I give you the equations and explain what to measure on each. There's 3 things that you're going to have to measure on the broad-crested weir. You're going to need to measure the critical depth using a pin gauge, and I'll show you how to use that. The weir length using a ruler. That's going to be the width of the channel for the weir length, L. And then the flow rate, you're going to use the stopwatch and the volumetric method that you've used dozens of times before. And then if you switch to the back page, it shows the image for the contracted rectangular sharp-crested weir. Again, you'll measure 3 parameters. You'll measure the water depth, the weir length, and the flow rate, and then from that be able to calculate both the discharge coefficient and how does that compare to the typical discharge coefficient of 3.32 in SI units. Okay, so we've got about half an hour to do the lab demo. I think that'll be a good amount of time. We won't be too pressed for that at all. Are there any questions you'd like to ask before we conclude here in the classroom and go take a look at what's going on in the lab? I'm going to hand back your homework assignments while you're in the lab. I've got them back from the graders, so if you want to bring your backpack to put that in, that's fine. We will reassemble in the lab in just a minute.